two important application laws that can be used once you know how to find inverse trigonometric functions. It's the law of sines and the law of cosines. And these help you solve triangles that are not right triangles. And these are the equations that we're going to use. There are different methods and ways that you can kind of generate these if you want to, but I'm just going to jump in and be like, this is how you use them. So the law of sines says that it must be proportional, that the sine of the angle over the side opposite of it must be proportional to any other of the same type of outcome. So what that means is like sine of 50 degrees, which is not a known angle, I'm going to use my calculator for that, over 10 must be proportional to, and then the only other thing I know here is this angle here. So the sine of 30 degrees over C. Now you can only use this if you have one unknown. So while it would be true that the sine of 50 degrees over 10 is also proportional to the sine of what's called angle beta over B, here I have two unknowns, so there's no way for me to solve this. All right, we're going to cross multiply. And then divide by the sine of 50 degrees. All right, we do know the sine of 30 degrees. Right, it's 1/2. So C equals 5, 10 times 1/2 over, let's see, I'm going to use my calculator here to find the sine of 50 degrees. And it's 0.766. And so we get that C, let's just go to, nearest tenth, so 6.5. Now, one thing that I could do here is I know that this is 50 and this is 30, and all your angles have to add up to 180, so that's 80. So I do know that B is 100. So with just a little bit of some triangle work, I can now say, okay, well, beta is 100, and so sine of 50 over 10 is sine of 100 over B. Again, I'm going to cross multiply and divide. All right, sine of 100 degrees is 0.98. I'm going to multiply that by 10 and then divide that by 0.766. And I get 12.9. All right, there is kind of a tricky part of this though, when you have two sides and an angle, or I like to write it as angle side side. Okay, these ones are a pain in the butt for sure, because there's some different possibilities. Well, it is possible that you end up like having a right triangle if that side A is the same as the like perpendicular height of the triangle. If it's less than the height, then you have nothing. But then the kind of a pain here is when it's less than the height, but also less than B, because if it's bigger than B, we just have one triangle. But it is possible, because all I know is this, this, and this, that I end up having another possible triangle that would have those same side lengths. So not all triangles in this way are going to be congruent. So I'm going to have some kind of some different answers potentially here for gamma. Okay, so let's go ahead and think about what beta would be. Okay, and beta would then also be potentially something like over here as well, right? Like if beta was over here. So let's solve for beta and just kind of see what happens here. Okay, so I know the sine of 35 degrees over 6, sine of alpha over a, must be proportional to whatever the sine of beta is over 8. Let's cross multiply. And divide. And so I need to know what the sine of 35 is. Times 4 divided by 3. And so 0.76 is equal to the sine of beta. And then I need to be able to take the inverse sine of that, which on your calculator, because you wouldn't know how to do that necessarily without the calculator, you end up getting 49.9. But that's really weird because in the way in which this original triangle is drawn, maybe I'll even like erase this piece here, beta definitely looks obtuse, not 49.9 degrees. So by doing the sine of this angle here, I believe that this calculation is actually giving me that other type of triangle. Where this is 49.9 degrees. Well, because of the supplementary characteristics between what this angle would be and beta here. There is a little bit of some geometry that can come into play. This would be like an equilateral triangle. So if this is 49 degrees, not equilateral, excuse me, isosceles. If this is 49 degrees and this is 49 degrees. So then the other beta angle we can find by doing 180 minus 49.9. Which ends up being 130.1. So we have two different triangles in which this is true. So we have like a original triangle, and then we have like an alternate possible triangle, which makes this a little bit crazy. You could then also solve for gamma here, gamma here in that triangle. And then once you do that, you can solve for two different C's. I don't want to spend too much more time on this. I just want to make sure that you guys see kind of that like this type of triangle can be tricky, and you would have two different triangles that you're solving for, and can be quite the pain in the butt, if you will. All right, let's talk about law of cosines to finish up here. So if I was to approach this example and I'm like, okay, well, yeah, law of sines, sine of 30 degrees over b must be sine of alpha over a. Well, I can't solve that. And I don't have another angle even to be like, oh, well, I just need to take some, triangle rules here. Like, no, I can't solve this. So I need another equation set up. And again, there are like different proofs of why these equations are what they are. But since we know beta, we're going to use this one right here. So use the one that only is going to have one unknown. And so we're going to say b squared equals a squared plus c squared minus 2 times a times c and then the cosine of 30 degrees. You would definitely want a calculator for these. Like, these are not going to be nice numbers per se. So we'd have 100 plus 144 minus 240 times the cosine of 30 is root 3 over 2. So this would be 120 root 3. So I end up getting b squared is 36.15. And so when I take the square root of that, I know that b must be 6.01. And then you can solve for the other angles using inverse trig and using that b value here. Or you could even use law of sines at that point, because now I know that actually might be what I would do. I know that this is here, and then I can use law of sines versus like this is kind of yucky to solve for this. So 10 sine 30, oh my goodness. Is this here. Divide and then take the inverse sine of this number to find alpha. All right, one more example of what you would need to do if you had maybe, so this would be like a side angle side example. What if we had all three sides? Then it doesn't really matter which one of these you use. Like, let's just solve this for alpha. So a squared equals b squared plus c squared minus 2bc cosine of alpha. Let me just double check and make sure that perfect. Okay. So you have to do this for two angles. Again, you could then, once you've done it for one, you could use law of sines for the other ones. And I'm just going to go through this one example here on the problem so that you can see how to work this. But it's literally, once you figured out which equation you're going to use, you just plug in. My pen is kind of going out here, y'all. Sorry. Okay. So 425 squared. 625. 18 squared. 324. 900 cosine of alpha. So this is 949. When I subtract that over and then divide by negative 900, I get 0.61 equals the cosine of alpha. And so you'd have to use technology here. Alpha is the inverse cosine of 0.61. And that's how you use these formulas. They're very straightforward formulas, just the problems in which they solve aren't always nice and straightforward.